So let's go ahead and start our implementation. We're gonna do the same thing that we did before, but instead of creating a linear model, we're gonna create a very simple artificial neural network. We are not gonna use any activation functions. So this neural network is gonna be linear. So we're basically using an artificial neural network to do linear regression. It's overkill, of course. In reality, you don't need to do that. If your data is linear, just use any type of linear model that is simpler than an artificial neural network. But just for sake of learning, we'll be demonstrating on how would you do linear regression using an artificial neural network. And then for our next practice, we're gonna make a nonlinear model, of course. That's what the neural networks are for modeling nonlinear data and complex data. So the very first thing we're gonna do, we're gonna be working with TensorFlow, as I mentioned before. So we have to import that package. And just to shorten the name, since we're going to be using this package many times, you're just going to call that TF. So we can use TF instead of writing TensorFlow all the time. All right. So since this is the first time, it's going to ask you if you want to run anyway. That notebook can run it. It's going to initiate the session. So the sanity check again, we can print the package version just to make sure it was loaded and it worked well. Looks all right. So this is the version 2.8. Looks like the package was updated since the last time this documentation was created. And we're going to do the same thing, simulating our data as before. We're going to add a little bit more samples just to increase the complexity a little bit, because now we are using a more robust model, and we're going to fit things automatically now. We are not going to fit things from scratch. So we hope that with 100 samples and a little bit of noise and bias, we should be able to fit our data using the optimizer automatically here. So let's plot our data to see how it looks like. Compared to the data that we saw previously, it's just a little bit of more samples and a little bit more noise. And here we have a positive slope. We did not multiply y by a negative number. So let's keep going here. And here's the moment where the linear regression is very different from what we are doing here with TensorFlow. TensorFlow, as I mentioned before, it doesn't work with vectors or scalar values or arrays. We have to convert our data. So then TensorFlow can use this organized structure to feed your data into the neural network that is also in tensor format. And also because only through tensors, to this tensor data format, to this type of variable, we can leverage the power of GPUs. That's why it's important. That's why TensorFlow only works with tensors. And the function from TensorFlow that we're going to be using for converting your data to tensors automatically, you don't have to do multiple steps. It's just one line code to convert your X and Y into tensors, is the function from tensor slices. And that function belongs to the sub-module data set that is in the sub-module data from the package TensorFlow. And that's what it does. It takes your data as a tuple, your X and Y. Your data can be a vector, a matrix, NumPy array, or any sort of numeric format. Usually we work with NumPy arrays or with a list or vector, as we were doing right now. And we just provide that as input arguments in a tuple like that, in parentheses. And this function will be responsible for doing all the job of converting our data into a tensor. So that's the syntax. You use this whole subset of modules and this function to provide your data as input. In our case, we are providing as input our simulated data for this course. But whenever you are working in your real world project, you don't need to provide simulated data. Of course, you can provide your own data as only as it's a numerical data, right? It would not accept strings or characters. You have to convert everything to numerical variables. So if we have some more explanations here, more details, if you want to go through the documentation. And now that we have our data simulated, generated, and converted into tensors, we can start to work in our linear models. We're going to work in building our first artificial neural network. And the function inside TensorFlow that does that is the sequential function inside the model's submodule within the Keras submodule of TensorFlow. You're going to see that TensorFlow has many submodules that have functions. Unfortunately, it's the syntax of TensorFlow. It's a very big package with many collaborations with different groups that develop different functions. So that's why it's just it's a huge tree of submodules. So I'm gonna have to get used to writing down those sub modules. And this sequential function, what it does is to create an empty model. So that's how it works. For building our artificial neural network, first we use the sequential function to create an empty model, and then we start to add the building blocks of that neural network. We start adding layers, we start adding activation functions, we start to choose what kind of optimizer algorithm we want to use, and then we decide fit our model to the training data. So that's the basic workflow. So first we're gonna create an empty model. We're just storing that empty model to this new variable here, model. It could be any name that you want. And once we have an empty model, it doesn't have any layers. It doesn't have any neurons at all. So the first thing that we have to do is to add our hidden layer, our layer of neurons, right? Our first hidden layer in the neural network. For adding that layer, now our model object has a subfunction called add. That add function, what it does, it adds layers or activations, adds elements, items to our model. In our case, what we want to add is one single layer of neurons. And since we are here trying to reproduce the simplest type of model as possible, just a simple linear regression model, but in neural network form, we just gonna set this layer as having one neuron. So we are creating the simplest thing as possible. It's just one artificial neural network that has one layer with only one neuron. And how we add a layer? So we use the dense function that creates a densely connected layer. This function belongs to the submodule layers from Keras as well within TensorFlow package. And the input arguments for this dense function for creating our layer is how many neurons we want to have in this layer. So basically, we are just simulating a simple linear model with one neuron. So we are setting an units of one, and we have to specify also the input shape. In our case, we have a rank 1 tensor. Remember, we have just one dimension. We have one set of predictors. We don't have a complex data that has width or height or subfeatures. We only have one predictor, so it has a rank 1, basically. It's just one set of features. If we had more set of subfeatures, we would increase that number of dimensions. All right, so let's add a single neuron with just a simple hidden layer with a single neuron, specifying the shape of our tensor. And if you want, for example, to add more neurons later, if you're playing with the data, if you set a units equal to, we're gonna have 2 neurons, for example. And that number can increase as much as you want. Of course, as you increase the number of neurons, you're increasing the complexity of your neural network. So your neural network would be able to model more complex data. So that's how you start tweaking your neural network. And you can also add more layers of neurons by using the add function. So if you run the add function again, you can keep adding more and more layers as well. And that will also increase the complexity of your neural network. The next step here, if you want to do some sanity check and some debugging, let me see if I didn't forget to run. Okay, I already ran. I have the check here. So if you want to show a summary for a sanity check to see how your neural network model looks like, you're gonna see some specification. For example, it's gonna show you the layers that you have in your neural network. What is the layer type? We have a densely connected layer. What is the out shape? We have a rank 1 tensor, and none just represents that we can use any batch size that we want. So we have no specifications for how many samples we're gonna train at once, and then the number of trainable parameters in our model. So we have 2 parameters in our model, 2 parameters that can be adjusted. One is the model weight, that slope that is multiplied by x, and the other one is the bias, is the intercept. So those are the 2 things that we were playing with manually before. We're just adjusting by hand. Now, those are the two things that will be adjusted automatically. And finally, we can specify the loss function. I already described before. What was the loss function? We're going to use exactly the mean square error, the same one that we used before. But this time, since we work tensors, we have to use the mean square error function that comes from TensorFlow, because this function expects to calculate the mean square error using tensors, using the GPU. So we are not going to use the sklearn mean square error just because it doesn't support working with neural networks. So let's define that as well. This one is easy. It's pre-implemented as the mean square error function inside the losses submodule. If you want to play with other loss functions in the submodule, you can go to the documentation of this submodule in Keras, and you see all sorts of loss functions. And depending on how your X is associated to your Y and what is the range of your Y, you may play with different loss functions. For example, if you have a dichotomous 0-1 classification problem, you may use cross entropy, binary cross entropy loss, instead of using the mean square error. That is more typical for continuous values. So you can also tweak that. The loss function type you use is also a parameter that you can tweak. And finally, we're going to choose what is the optimizer algorithm. So the part that we did manually before, adjusting by hand, now it will be performed automatically by the optimizer. And the default optimizer that we're going to choose is the stochastic gradient descent. There are different types of algorithms for optimization. I'm not going to go too much detail on the calculations that it does, but different types of algorithms may do better on different types of data and different types of associations between X and Y. So that's another parameter that you may want to tweak. You may want to change what type of optimizer you use. So finally, we can choose our optimizer. This is what is going to optimize the weights and the bias. It will adjust the parameters of our model automatically. So we're not going to do this by hand anymore. And finally, the model compile is the function that the subfunction within our model that adds the optimizer and the loss to our model. So our model had only a layer of one single neuron before and the inputs, of course. And now we are adding both loss and optimizer that we defined before into our model. That's how we usually do in this workflow. Create an empty model, add the layers, add the optimizer, add the loss with the compile. And then I think we are ready to train. And the part I wanted to go in a little bit more detail was on the model training steps. As I mentioned before, a training step or a training iteration consists of initializing the weights at the very first iteration at the beginning. All the weights are randomly at the start. And then we calculate the loss or how wrong the model is given the current weights. Then the optimizer computes the gradients. It points to the right direction where the weights should be updated to decrease its loss. And then we update the weights, and that's one pass through the data. That's one iteration. And then we go back to the step 2. And we keep in this cycle over and over until there is no more improvement in the loss, or until we reach maximum number of iterations that we can set in the model fitting step. So before we can fit this model to the training data, we also have to split this training data into batches. A batch is how many samples are processed before updating the weights. So let's say we have a data set with 100 samples. We split it into 10 batches of 10 samples. We're going to update the weights 10 times after seeing batches of 10 samples each time. That helps to optimize the algorithm because we have more updates. We have more chances of finding better weights in the model and finding better solutions. If the batch is too small, though, it could generate too many fluctuations in the data. So you kind of have to adjust that batch size to your problem, to your data set, to your complexity in your data. And just another term that you're going to see many times is an epoch. An epoch is when you complete one pass through all the batches. You did all the weight updates for all batches in your data. So that's one epoch. You can train your model for as many epochs as you want. The recommended is to set a certain number of epochs that will not waste time, that will not be stuck into the same loss value over and over, and that is not too small, that the model will not converge, it will not reach to a good solution. So that's another parameter that you kind of have to start at a certain value and then try to increase it, decrease it, and see if that helps your model to find the best solution and not overfit. So back to our model training here, I have a more detailed documentation here explaining what is a batch, what is an epoch, showing many examples. If you want to read through that, could be helpful for better understanding this in more detail. So here is the moment where we take our data and we use the sub function batch to split our data into batches. And the input argument to this function is the batch size, how many samples we want to have per batch. Here our batch size is 10, so we're going to have 10 samples per batch. So our data now will not just be one whole thing with all the samples, it will be split into chunks of 10 samples. And then the model during the fitting process will understand that every time it sees 10 samples, it will be the time to update the weights and compute the gradients. So now finally that we have our data already converted into tensors, we have our data split into batches, and we have our model built and compiled, we can do the model fitting process. Here we use the fit function, that is a function that belongs to our model that we built before using the sequential function. And it takes 2 or more arguments. The most essential required arguments are your data, which we built before from the simulated data that was converted into tensors and split into batches, and the number of epochs that we want to train, how many passes we want to do through all the batches, updating the weights until we stop training. So we're gonna pass through all the batches, updating the weights 100 times. And we can start running the training. It will show you a report. It should be pretty fast. It's a very small model, and it will show here that it completed all the training steps and it reached a loss value, an error of 104. Last time we were updating the weights manually in the linear model, and we reached something a little bit less than 200, I think. So this loss is already much better. Of course, automated and optimal algorithm for optimizing the weights is much better than our gut feeling of trying to see if we are warmer or colder when we were trying to manually update things, right? But it was a good experience to understand what is really happening here in this training process. So after that, we can use the predict function from our model to take the pre-trained model that we already trained before. Now this model is trained, it's fit to the data, and we can use the function predict on our X values or predictors to generate our predicted response results. So we have the ground truth Y values, which we generated from simulated data. We also have the X values, the predictor values that we generated from the simulated data. And we use that data to train our model. And now we can use the function predict to see what are the predictions of our model for the X values used in the training data. So we're gonna have the Y hat, that is our predicted version of the Y after the model was trained. And we generated that, so then we can plot the X values versus the ground truth values that we generated from the simulation. And we can also plot the X values versus our predicted values generated from our model after training. And this is our result. We have the blue dots here representing the simulated data. And then we have our linear neural network of one single neuron in orange here. All the predicted values fit to the training data. So this is very similar to the result we would get with a linear regression model. So this was just a demonstration on how we would implement the simplest possible type of neural network with TensorFlow. So now that you know how to implement a very basic and simple neural network in TensorFlow, you have the basic building blocks to start making these models more complex. And we're gonna get into that in our next practice, we're going to start to make nonlinear models by adding nonlinear activations to the layers. In addition to the hidden units, we're going to specify nonlinear activations. We're going to also, in the future, start to play with the number of units, with the number of neurons, and we can also add more layers.